Welcome to The Explainer. Today we're diving into a cosmic detective story that challenges, well, pretty much everything we thought we knew about astrophysics. We're going to travel all the way back to the very dawn of time to investigate a missing puzzle piece. And it's a piece that might just explain the fundamental makeup of our entire universe.
So, could a black hole seriously have the mass of a paperclip? I know, it sounds totally absurd, right? Whenever we think of black holes, we usually picture these massive, terrifying cosmic vacuum cleaners just swallowing up entire star systems. But what if I told you that our universe might actually be swarming with black holes so incredibly tiny you couldn't even see them with a microscope, yet they pack the mass of a mountain, an asteroid, or yes, even a paperclip? This isn't science fiction. This is the mind-bending reality of primordial black holes.
Section 1. A cosmic mystery unfolds. 3 massive anomalies.
Okay, let's dive into this. To understand why scientists are hunting so hard for these bizarre objects, we first have to look at the massive headaches currently plaguing modern astrophysics. Cosmology is haunted by 3 really big mysteries right now. First up is dark matter. It literally makes up most of the mass in the universe, but we have absolutely no idea what it actually is. We just know it pulls on things gravitationally. Second, our observatories keep picking up gravitational waves. These are ripples in space-time, from colliding objects that actually have less mass than our sun. And according to standard stellar physics, that shouldn't be possible. Third, the James Webb Space Telescope is out there spotting ancient galaxies that are just way too massive, way too early in the universe's history. They literally shouldn't have had time to grow that big. But here's the kicker. A single ancient suspect might actually connect all 3 of these anomalies.
Section 2. Born in the Big Bang. Primordial Origins.
To find that suspect, we have to go back, way back. Not just millions of years, but to the literal beginning of everything. We really need to draw a huge distinction here. The black holes you're probably used to hearing about, stellar black holes, they require a dying star. A massive star runs out of fuel, its core collapses under its own gravity, and boom, you get a black hole. And because it comes from a star, it has to be huge, always greater than one solar mass. But primordial black holes, they play by entirely different rules. They don't need stars at all. They form directly from the extreme gravity and pressure of the dense primordial soup of the early universe. And because they skip the collapsing star phase entirely, they can theoretically be absolutely any mass whatsoever.
Looking at the timeline of the cosmos, primordial black hole formation happened in literal fractions of a second right after the Big Bang. During a period called cosmic inflation, space itself expanded faster than the speed of light, taking these microscopic quantum fluctuations and stretching them way out. If one of those stretched-out pockets of space happened to be just a little too dense, the crushing pressure of the early universe collapsed it directly into a black hole. Notice that stars didn't even exist yet. They wouldn't show up for hundreds of millions of years. So these black holes predate stars entirely.
I love how the research papers describe this formation process. They call it a non-linear race against sound waves in the primordial plasma. It's a great visual. Imagine the early universe as an incredibly hot, dense soup. If you have an overdense pocket of matter, gravity desperately wants to pull it all inward to form a black hole. But at the exact same time, intense outward pressure, moving at the speed of sound, is trying to push that matter apart and disperse it. It was a literal cosmic race.
And that brings us to a really crucial number, 1/3. The math basically tells us that if a specific region's density contrast was exactly at or above this 1/3 threshold, gravity won the race. The outward pressure just couldn't push the matter away fast enough, and the region instantly snapped into a primordial black hole.
Section 3. Vast mass scale, asteroids to supermassive. Because these fluctuations in the early universe could happen on practically any scale, the resulting black holes are all over the place in size. It's like a giant puzzle falling into place. We have microscopic ones, which we'll talk about in just a second. Then we have asteroid mass black holes. These could absolutely be the dark matter we've been looking for. Next are subsolar masses, meaning lighter than our sun. These perfectly match those weird gravitational waves we're detecting. And finally, we have the intermediate or supermassive seeds. If giant black holes formed instantly in the early universe, they could have acted as gravitational anchors, pulling in gas and rapidly growing those overly massive early galaxies that the JDST keeps finding. That's one theory offering 4 perfectly slotted solutions.
Hold on, though. Before we declare the case closed, we've got to talk about Stephen Hawking. He theorized that black holes aren't actually entirely black. Thanks to quantum effects near their edges, they slowly emit particles, which is a process known as Hawking radiation.
As they emit these particles, they actually lose mass. They slowly evaporate. And the smaller the black hole is, the faster it evaporates.
Which brings us to this mind-bogglingly tiny number, 10 to the negative 16th solar masses. The research tells us that any primordial black hole smaller than this threshold would have evaporated completely by now. They simply couldn't survive the 13.8 billion years to make it to the present day. So while the universe might have been filled with microscopic black holes right after the Big Bang, many of them have probably just popped out of existence, releasing a final flash of gamma radiation as they went.
Section 4. Dark matter connection. The missing mass.
So the microscopic ones might be gone, but what about the ones that survived? Wrap your head around this staggeringly huge possibility, 100%. For decades, physicists have been building these massive underground detectors trying to capture an exotic, invisible dark matter particle. But right now, there is a completely open window in our observational data. Primordial black holes roughly the mass of an asteroid, so between 10 to the negative 15 and 10 to the negative 10 solar masses, they could account for all the dark matter in the universe. Think about that for a second. Dark matter might not be an undiscovered particle at all. It could literally be trillions of ancient, invisible black holes quietly flying through our galaxies.
Section 5. Hunting ancient ghosts. Active detection methods.
So, how exactly do you find an invisible object the size of an atom that weighs as much as an asteroid? You obviously can't just point a telescope at it. You've got to get clever. We currently have 3 main traps set. First, gravitational wave observatories like LIGO. We listen for the ripples in space-time when 2 of these black holes crash into each other. Second, microlensing. If a tiny dark black hole passes in front of a distant star, its gravity acts like a magnifying glass and briefly brightens the star's light. Upcoming telescopes like Roman and Rubin are designed to spot exactly those tiny telltale flashes. And third, gamma rays. We actively look for that final explosive flash of Hawking radiation as the microscopic black holes finally evaporate and die.
And here's where it gets really exciting. We might actually already have a smoking gun in the data. Event S251112CM. This was a gravitational wave candidate detected back in 2025. The analysis showed that at least one of the colliding objects had a subsolar mass, meaning less mass than our Sun. Remember our earlier contrast? A dying star literally cannot create a black hole that small. Standard astrophysics has no easy explanation for an object like this. But a primordial black hole? It fits the profile perfectly.
Section 6. Rewriting the story. Cosmic implications.
If we can definitively prove that an event like that was a primordial black hole, or if our new space telescopes detect the microlensing signature of an asteroid mass black hole, it genuinely changes everything. And the theories actually get even wilder. Some of the latest research into quantum back reactions suggests that Hawking evaporation might not actually destroy a black hole entirely. As the black hole gets smaller and smaller, the extreme curvature of space might halt the evaporation process completely. That would leave behind a Planck-scale relic, a permanent, microscopic fossil embedded in the fabric of space. This means the universe could be absolutely littered with these tiny, undetectable remnants. Actually, to put that into perspective, if a microscopic primordial black hole passed right through Earth today, its gravity would be so localized and it would be moving so fast that it wouldn't swallow the planet. It would just leave a microscopic, basically undetectable seismic wake as it exited out the other side. Wild, right?
Which leaves us with one final, absolutely wild thought. For years, astronomers have noticed these weird gravitational anomalies at the very edge of our solar system, pulling on icy rocks out in the Kuiper Belt. Many believe this is an undiscovered Planet 9. But researchers Schultz and Unwin proposed a radical alternative. What if Planet 9 isn't a planet at all? What if a grapefruit-sized primordial black hole was captured by our Sun's gravity billions of years ago and is quietly orbiting in the dark, right in our own cosmic backyard? As we keep searching the skies, we really have to ask ourselves, just how close might these ancient ghosts really be? Thank you so much for exploring this incredible cosmic mystery with me today.